we are talking to Odin, and he's look like young, very young, but he's really the god of metaprogramming in C++. And feel free about the all question which is connected with metaprogramming in C++ because this is in other audience and other room that is not available, only here, only now, maybe in 1 hour, of course, after the presentation. The presentation was about the bare metal chips and the API which is using it. So, Odin, please, your voice.
Okay, obligatory question. Who am I, what am I doing here? 2 parts. First one, nobody really cares. She already introduced me. If you want to know more, CPP cast. Next question, what am I doing here? Yeah, they must have really low quality standard. No, I'm kidding. No, what I'm really here to do, I work on, very small bare metal microcontroller systems. And that domain is completely dominated by C and still some assembler guys. There's very few C++. There is a little bit of like C++, as in like, okay, we use classes, we use namespaces, but function overloading, that's still kind of scary, right? So, there needs to be code sharing possibilities. There needs to be, embedded shouldn't be a domain where you have to have like 5 years prior experience in embedded to get a job, right? There needs to be more of a free flow of programmers between these domains. And this domain may sound like a total niche, but that's because of this phenomenon. Like, there are a lot of embedded developers at some of the bigger embedded companies, Siemens, Bosch. Like, there's as many software guys as like Microsoft or something, but you don't really know. I mean, it's the same order of magnitude anyway, but you don't know because what software do they make, right? Okay, it's embedded, it's in your car, it's in your nuclear plant, right? That probably shouldn't fail. So this is an API talk, and there have been a lot of API talks. There's no sense in doing another API talk unless you're going to do something new. And what we know from most API talks is, okay, they last forever. You have to get it right, But like, what is right? Like, a lot of API talks, they'll defer to, oh, Qt is a great API. Look how long they've been an API, and look how intuitive it is. And yeah, well, we can't really do that if we want to make a modern API, right? Because if something's been around for 20 years, it's a good example of a good design decision 20 years ago with the tools from 20 years ago, right? So, Qt made a very sort of usability-oriented design decisions, and it's worked well for them. Boost has made more performance-oriented design decision, especially execution speed oriented. And arguably, there's a lot of Boost libraries where you'd have to learn a lot more before you can actually use it than, say, Qt, right? Like, if you want to use Boost Spirit, well, I don't know, take me a while. So what makes a good API? Like, are there like because usually if you want to do something new, it's good to take a more first principles approach, right? What are our goals in general as an API designer? And how well we achieve those goals depends on our tools and our design decisions. And if you think about, okay, if I were a marketing guy, this would be a nice like word cloud, right? But I don't like word clouds. I'm also not a marketing guy. If you think about stable, this is really a composite, right? Like, if we make good trade-off decisions, safe versus zero cost, right? If we change that decision and say, okay, well, we want to be more performant and maybe less flexible or maybe less teachable, then that makes an unstable API, right? Because we have to change things later, right? If we don't worry about extensibility, can we improve on this library, then that makes an unstable API because we have to change it, right? It's not a goal in and of itself. It's a product of how well we make design decisions. And what design decisions we make, I will try and highlight throughout this talk, depends very much on our tool set, right? I mean, almost all choices in software are false choices for lack of better tools, right? Composability is usually left out of these kinds of decisions, except for, C++, right? I was just at Vicente Bote's talk about, how much effort they're putting into extending what we have in C++ and not breaking things, right? And making so it's still kind of intuitive how you work with code that was, APIs that were designed like when I was still in diapers, right? Like, sorry for that. No. So how have we done, right? Okay, standard allocators are kind of a fail, but on the other hand, it's good that we have something. Like, this is probably one of the first, at least very public cases of policy-based class design. How many people have heard of policy-based class design? Okay, good crowd. It was popularized by Andrei Alexandrescu in his book in 2001. That's a long time ago now. But there are still very few examples of it. Standard allocators are not a very good example of how it's done well, but it was very early, right? Standard stream performance issues because we used virtual functions. We probably shouldn't have done that, right? We're fixing iterators. We also have flexibility problems. If I want to use a standard function, and I'm in a highly multi-threaded environment, so I don't want to be using the heap, because the heap is essentially a global thing with a lock around it, right? At least most of the time. Say I have a function object that's the size of 4 pointers. That's probably 1 pointer too big to take advantage of small object optimization on standard function, right? Anything 3 pointers or less, it'll actually go on the stack, and if it's more than that, it'll go on the heap, right? But that's implementation defined. That's standard library implementation defined. If I could hack one of the standard libraries and change that, but then I'd have lock-in to my hacked version of the standard library, right? Why can't I define that as a user, right? Why can't I add a template parameter that says, okay, this is how big small object optimization should be, right? It's a flexibility problem. This is actually very bad. You could be relying on small object optimization because your object is 3 pointers, and then get terrible multi-threading results if they ever make it 2 pointers, right? Because suddenly these objects that used to be going on the stack are now landing on the heap, right? And you have no real control over that, right? So there are flexibility problems, right? If I can't customize it as a user, then I'm locking myself into some implementation details, right? And you don't upgrade compilers very often. You don't switch to another system very often in like desktop development, right? Like, okay, compile it in x86. That still works, right? In the domain of embedded systems, in my company, we're tiny and we already use many different chips, right? And these are completely different platforms, right? If you look at the amount of different chips that, some bigger company, how many different chips does Nokia use for their embedded stuff? Probably 1,000 or something, right? Like, we have platform switches very often. And so these things can come back and bite us. Node-based containers, again, there's an implementation part of that. I don't think people saw that coming, but back when they were designing these things, when, I was too shy to talk to girls, like from the chronological order of things, right? Back then, we didn't have the same caching architecture as we do now. So, we implicitly made design decisions that turned out to be Like, it's really hard to beat a vector in any kind of container. I don't care what the big O notation complexity is. Because of caching, vector is essentially always going to be faster, right? So, yeah, we failed. And, you know, in case you still need like a proof that we failed, okay, standard vector bool. I think I could leave it like that, right? Like if introductory books to C++ say don't use this feature that's in the standard library, then we failed, right? And in that case, we were trying to do too much, right? We were trying to make the API too sexy, right? Like, you know, I mean, standard vector bool today wouldn't pass what I call the Sean Parent test, right? Show Sean Parent, and if he doesn't gripe about it, that's a good smell test, right? This standard vector bool invalidates constraints or expectations that we have on types that are returned from a container, right? We want to be able to assign to it. We want to be able to take its address, right? In the case of standard vector bool, it's a proxy object, so all of that is invalidated. So we want to not do that in the future. So there are examples of good APIs, right? Like the STL. I mean, if the major fails fit on a slide, and you're a huge library, you did really good, right? Boost MSM I like because it's fast, right? Like Boost MSM before C++ 11 was essentially the metastate machine library. If you wanted to make a state machine and have it implemented in essentially the fastest way possible, you use Boost MSM. And with those very, very stringent constraints, I think they did a very good job of making the public interface usable, right? Like, you know, it takes a couple of days to look at it, and then you can actually use it. I think today we could do a way better job, and with the compilation speed Chris Uziak already has, there's the Boost MSM Lite now. I'm not going to say anything about Qt because they like to flame people that diss Qt. Boost Unit is one of my favorite examples of like a good API because they didn't try to do too much, right? Like, okay, it's a little bit ugly. We can do it better now, but with the tools they had, Boost Unit is very good. You know, absolutely zero cost. People like Cinder as kind of a modern API. I don't think, like, from the data it was designed, it's quite modern enough. But this is a bare metal talk, right? I mean, you know, that's a golf ball and a chip on a golf ball, right? Like, that costs €1 or less, right? I mean, we're at the very low end here, or we at least have to work on this low end of the Cortex spectrum. Cortex or ARM processors, they've already sold like tens of billions of them, and they're going to sell tens of billions more. I mean, I'm a little skeptical about a lot of these predictions about Internet of Things, but there's a lot more of these coming. And so this is actually a huge domain. But on the other hand, it's a very different domain than desktop, right? We have 6 orders of magnitude less RAM, right? Like on your desktop, you have, I don't know, 4, 8, 16, 32 gigs of RAM. These chips start at 4 kilobytes of RAM. And, yeah, I mean, okay, they do go up a little further than most desktops. But if you work at Nokia or Google or whatever, you got machines that have more RAM, right? I mean, if we're designing for, 1 million times less RAM, we're going to make different design decisions than for desktop stuff, right? Like the processor itself, the core, I mean, you could play Doom on that, right? If you had enough RAM and some graphics capability. But yeah, it's seriously RAM constrained and latency constrained. I mean, we're more deterministic systems, right? Like if your, I don't know, Chromecast is slow, then okay. If your airbag is slow, you're probably dead, right? So we have really, really hard latency stuff. I mean, the airbag is, a great example because it's very easy to visualize. Most of the time, it's more, if you don't make this latency requirement, then your buffer overflows. And you don't have enough code and you don't have enough RAM to implement a protocol that has any kind of retry, right? Or enough man hours, right? I mean, if you're developing with tools that give you, 100x worse programmer productivity, it'd be very expensive to make that protocol be able to retry or be able to detect things. So we have timing multiplexing a lot of the time, because these are a lot of the times very cost-sensitive applications and a lot of times very energy-sensitive applications. So poor bare metal guys, right? I mean, what do these absolute latency requirements in this tiny RAM mean, right? Like, exceptions is debated in very much other terms in the SG14 working group or in other working groups, like the games designers or the high frequency traders. They could turn on exceptions, but it's like, oh yeah, but we have 5% performance. 5% performance in a game, that's very valid, right? So they want to find a way to turn these off. But like, if you think about, you're out of memory, and so you throw an out of memory exception. Well, if you're out of memory, where does that out of memory exception go, right? It goes on what's called the emergency buffer. So there's a buffer reserved for exceptions. And if you use exceptions, it will be implemented on your chip, right? And that's 40 kilobytes, right? I mean, if I'm on a desktop, I don't care about 40 kilobytes, right? I just don't care. But if I have a chip with like 4 kilobytes of RAM, that's just not happening, right? Like even if I have 64K of RAM, that's still not happening. Yeah. So we can't use exceptions. Like turning them off is strictly speaking undefined behavior. And most compiler implementers will say, okay, well, if you don't actually ever throw them, like only when you actually throw them is it undefined behavior. Compilers are getting better at taking exceptions out if nobody ever catches them. Because essentially, if nobody ever catches them, then you could just do at exit, right? You can just leave because no one's going to catch it. You don't actually have to do all the, you don't have to walk the stack backwards in the same way. But we essentially, we don't even have an at exit, right? Like we turn the thing on and it runs until we pull the power, right? Destructors of global objects, those things never run, right? We never return from main, because what would returning from main be, right? That there's no, yeah. So without that kind of stuff, we could potentially optimize way more if we could prove that there are no exceptions being thrown and caught. We wouldn't have to turn them off. We would still be somewhat conforming. But again, flexibility. Right? With a standard vector, well, I could implement a custom allocator that never throws out of memory, right? It just goes to hard reset or whatever my go to safety mode or whatever the system requirements are when I actually encounter something exceptional. But with standard vector, what about index out of bounds, right? The compiler's probably not going to be able to prove that I can never go out of bounds. And I don't have like a traits class, or I don't have, any kind of policy class I can drop in there to say, this is what you do when you're out of bounds. No, it's an exception, right? Like if we had used policy-based class design more, I might have been able to do that, right? The heap, again, is a problem. We're going to get into that later. Threading, yeah, it's debatable. But if you want to be really deterministic, phase shift of the scheduler also plays a role, right? Or, again, the RAM requirements. We're going to get into that also later, right? So if I can't use the heap or exceptions, I mean, pretty much all the standard containers are out, right? So I'm just left with, standard array. And also, okay, the algorithms, they'll probably work, but, standard stream, Again, virtual functions. Well, why is that important? I mean, it's not only an opaque function call, so the optimizer is going to not be able to see through that. Sometimes with link time optimization, that's getting better, but it's still not in all cases. Biggest problem with virtual function or any indirect function calls is these bare metal systems are often checked with software that analyzes the assembler in order to statically prove things, right? Like, I mean, who here statically proves things about their software? No hands, right? This is not something we usually do, like actual mathematical proof that we're going to meet this latency requirement, or mathematical proof that unit tests are good, but there's even like legal requirements if you're making control units for cars, or if you're making in the medical field, or any other very critical systems where somebody actually may be dead if you crash. Then we have to prove things like, okay, you can't stack overflow, right? Or you can't overflow a heap under no fragmentation patterns. That's actually, obviously incredibly hard to do because, fighter jets or things where very prominent people have worked on the coding standard, they disallow memory allocation after takeoff, which is kind of, an indication that this is hard to prove that it won't cause problems. Like, if they're not allowed to do it, I mean, those things crash anyway, but probably for other reasons. And if we think about this, like, in the Internet of Things, we need that kind of reliability, right? Like, I don't want to wake up in the middle of the night freezing. And I guess, a medical friend of mine says you don't always wake up, right? Like, people might die if your thermostat thing just does weird stuff, right? So the thermostat has to crash less often than fighter jets. And the development costs of that thermometer have to be like 6 or 7 orders of magnitude cheaper, right? That's why I'm a little bit sort of the emperor has no clothes on this Internet of Things stuff, right? I mean, there's a lot of stuff that's been swept under the rug, and people do, presentations with all sorts of fancy buzzwords, right? And it's good for playing bullshit bingo, but I mean, I don't want to overgeneralize. There's people doing very good work in that field too, but a lot of the times it's like, yeah, okay, you implemented it on a network where you can't make latency guarantees, and on a system where you can't make fragmentation guarantees, and on a system like, okay, you have a light fixture now and it's smart, but it uses more energy than the light bulb, right? So, okay, that's a whole different world. That's like orders of magnitude easier than actually making it in a way that people are going to actually use it, right? So, I mean, we have to look at the tough questions of these domains, right? IKEA kitchens have better static checking than most code, right? Why? If I build a building, then I'm going to run that through a lot of static checks. And, buildings fall over a lot less often than software, right? And unit testing and a lot of quality control, and there are systems that work quite well, right? Like if you look at how often operating systems crash, then that's definitely diminishing, right? We're getting there, but I think we need to use different tools in different domains, because there was a lot of operating crashing back in the beginning. And, if that's my door lock and I'm locked out a couple of times, it's a lot more important, right? I mean, many of you probably, the older generation, you probably memorized your Windows 95 key, right? Like, it crashed often enough that you knew that thing by heart, right? We can't do that for these indices. So this is basically the domain of C now, right? Programmer productivity is terrible, but you can still see what's going on, except for the people that get creative with macros. But that's a whole nother. So basically, we have to start in ancient Greece, right? We have no knowledge, really, of how to do APIs in this domain or how to do libraries in this domain, right? I mean, we tell them, oh, yeah, that's archaic, that's older than me. But what are we offering as an alternative, right? I mean, people making design decisions now, okay, I have a greenfield project. What library do I use? Well, if there's one here that takes a lot of man hours, and then there's one here that's only theoretically possible, nobody's implemented yet, what's your design decision going to be, right? We can't just do the same things that we're doing on desktop. And there's a lot of pushback from C guys, right? A lot of it's like, yeah, well, I can do everything in C that I can do in C++, right? It's been a while since they've actually gotten new tools, right? So we have to look very, very far back if we want to show them that this is kind of a cyclical improvement, right? So if we're talking about going from like punch cards or I'm writing my own binary to assembler, what changed, right? I mean, the argument could be made, I can actually do things if I'm writing bits that I can't do in assembler, right? If I want to obfuscate my code and put like the second instruction of a two-word instruction in my code, it will be executed as a NOP, but I can push in data there. I can't do that in assembler. If I want to obfuscate, maybe I could run through that another pass with a bit of an offset and then interpret everything differently. But that's a very niche area, right? If you're doing optimization, well, the whole point is you can't write in assembler, right? The vast majority of things we still can write in assembler, and it gives us a lot of static checking, right? Like usually you wouldn't think about assembler and static checking, but like I can only express things for which I have mnemonic, right? If there isn't a word for it, I can't express it. The compiler will notice if I use a work register that doesn't exist, right? Because it understands what I'm doing. So it's also much closer to my mental model, how I think about it. I mean, I don't think in binary. Usually I think in letters or maybe even pictures, but so we're getting there, right? We didn't really cost us anything either. Okay, assembler to C. Well, that's actually, okay, you could argue Fortran was in there somewhere, right? But assembler to something where I have a way of expressing myself, but it's core agnostic, right? I can express myself and then have like a strategy pattern of how to generate assembler out of that, right? I can use my C code and compile it for this chip, and I can swap out the compiler and compile it for that core, right? So I added a lot of functionality. Again, it's much, much closer to my mental model. More flexible, better code reuse, more safe. Like it's very easy to screw up a stack frame if you're writing an assembler. It's quite hard to screw up a stack frame and not do something incredibly stupid in C, right? Like, okay, if you write over the end of or before the beginning of an array that's on the stack or something, you could screw up the stack frame, right? But it's pretty automatic. Like, I don't really have a syntax for expressing the wrong stack frame creation and destruction, right? I took that out of the things that I could express, right? And okay, I can express like things. Preparing for this talk, I was going to say C dictates that you have to use the stack, right? As soon as you call one function, you have to use a stack. And then I talked to a guy that like made arms for space robots, and he told me, yeah, actually there are compiler extensions, so you can actually make like all the variables static globals, and the return addresses are the only thing that goes on the stack line. Okay, there are exceptions, but for the most part, they dictated this design decision, and that was a good thing, right? Like, we build on the concept of a stack. It's commonplace, but it was a design decision that's essentially forced on us, right? But that's good, right? I mean, chips nowadays even have like, push to stack or call or whatever actually pushes some of the work registers, some of the registers stack in hardware, right? Like this is even in hardware now, this design pattern. And, okay, I'm starting to get a bit of the capability of creating my own code, right? Like, you could think of C as a code generator for assembler with swappable strategies. Well, I also have my own code generator. It's a terrible code generator, macros, right? But it's a code generator, and people get very creative with this in the embedded domain. Like, if you're looking at macro expansion, I mean, you can use the JetBrains compiler and see them expanding, but if you're going into like the 20th nesting depth, then yeah, chances are the person that wrote that doesn't understand it anymore, right? So yeah, this is kind of the last iteration that the embedded domain has gone through of these kinds of improvements, right? Like, okay, if I have an address and that address is a pointer to something and I add 1 to it, it's actually going to add the size of the object to that address, right? It works automatically. Wow, that's an awesome address. That's the last thing, like the last update that they've really had, right? And this is a long time ago, right? Okay, C to C++. And notice on the right-hand side here, I don't use auto, right? I'm talking about C++ pre-C++ 11. Again, essentially a code generator for C, right? And old implementations of C++ actually were a code generator for C. And that's important to know if you want to like intuitively predict what the compiler is going to do. Think, oh, could it do it in C? Well, if not, that's probably not how it does it, right? Because at one point it had to do it in C. I have more static checking possible now, right? I can make objects my own type, not screw a lot more stuff up. I can start to use templates, right? I mean, it's not a full-blown code generator yet, but people did some pretty cool stuff with templates. Okay, the STL, as I said earlier, it dictates some design patterns, right? I essentially have to use exceptions for the vast majority of the STL. But the core language is still completely opt-in, right? If something's too expensive, I don't have to use it, right? So essentially, you can take your C code and compile it with a C++ compiler, and very little breaks. And where it does break, where you're just implicitly converting to avoid star or something, it probably should break there. You probably should like add some information there, right? So Dan Sachs is a very big proponent of this. Just take your C code and compile it on a C++ compiler, right? Turn off exceptions, strip runtime type information. Do the stuff that's going to make it fast. There are pitfalls if you just take like a compiler and just say compiled, and you're like, wow, where'd all my RAM go? Yeah, well, you didn't turn off exceptions. You didn't just strip RTTI, right? But so that there is a bit of a foundation for these performance myths, but there have been talks at other conferences about how, okay, if you take C and compile it on C++ compiler, some of the time it's actually even more efficient, right? If you actually start using templates rather than macros, well, some of the time that actually even gets more efficient, right? We're not losing efficiency here. And we're gaining a lot of stuff. But we're in C++ 14 now, right? Like, we can assume that C++ 11 is available. And I don't think people realize how much template metaprogramming improved as of C++ 11 and other things that have happened in the last couple of years, right? I mean, if you look at MetaBench, which is Louis Dion, the actual god of metaprogramming, I have no intention of taking that title away from him. Yeah, he made this MetaBench where you can actually benchmark compile time of different algorithms against each other. And for many algorithms, it's actually 100x, especially if you take into account, okay, 5-year-old compiler, 5-year-old desktop, 5-year-old language standard. You're going to get even more speed increase, right? And we're still discovering things, ways to make template metaprogramming faster. I'm doing a lightning talk at Meeting C++ if you're interested. So now I can build my own code generator, right? Like, it's a code generator that generates code for a code generator that generates assembler. And I can make a code generator that generates code for that, right? At compile time, I can make decisions. It's completely Turing complete and now fast, right? And because of things like auto and lambda and HANA style, which is essentially, like, how many people know of Boost HANA? Okay, couple. The big improvement of Boost HANA over previous libraries is that it allows you to call meta functions, as in functions that are happening at compile time in the compiler, with much the same syntax as we use for normal functions, right? So I can make a templatized function and call it with some templatized types, extract those template parameters, and call normal meta functions with that, right? And so we can get syntax that's kind of like this on the right side, right? Like, okay, forget about like how we're doing this kind of stuff, right? This is a function call. What does this function do? I mean, the C equivalent wouldn't fit on all my slides, right? But it's pretty intuitive. Like, okay, if you're not, in the USB domain, vendor ID, product ID, okay, what's that, right? And what's a CDC? Well, that's in the USB standard. It's a communications device. So it's basically a virtual COM port, right? My virtual COM port. Initial baud rate. Okay, if nobody configures it, what's the baud rate, right? These are things that are known at compile time, so why don't we leave them at compile time, right? We can get to a very intuitive interface, right? Like if you wanted to say, how many stop bits does it have initially? Well, where would I change that? Well, I'd probably just add it here, right? Right next to the baud rate. If I wanted to be two devices at the same time, where'd I add that? Well, I could just CDC and then a comma and then the next device. I could be, a serial port and a human interface device, right? So how do we implement this kind of thing, right? Like this doesn't look like we're feeding a template monster, right? But essentially everything we pass in here is known at compile time and just should stay that way, right? None of this is going into any kind of runtime decisions, right? This is going to become a const x per string, right? And even if we actually have to change this, because we're not passing a string directly, we're putting it in a larger array, we have to make it multi-byte characters. We have to do different things to it. We can do that at compile time and just make our own second const x per string at compile time, and the compiler will get rid of the first one, right? Because we only use it at compile time. So, at AutoIntern, we implemented a USB stack because all the other USB stacks that were out there had bugs and don't like our weekends or whatever. And it turned out to be, half an order of magnitude better than the best implementation as far as speed. And then, that's a false comparison because we handle things like, oh, you slept, or, oh, like you have a race condition. Well, if you were to take out that race condition, that would cause a lot more code, right? So we're probably better than, a couple X better. So, you can definitively prove that you can beat typical C or, industry standard C. And Jason Turner has a talk about modern C++ on the Commodore 64. And I believe he also beat the assembler that they wrote way back then, right? Because we have powerful tools, right? We have an optimizer. So this is the example of HANA style. This is the first thing we're using, right? And then, this is the example in the README on the HANA library. If you want more information, go check it out. You can actually do metaprogramming. Like, who knew that? Look, you can actually do type calculations at compile time, and it looks like you're using runtime, right? Okay, I have to say 1_C. Now, _C in that case is a user-defined literal that parses that string, turns it into a type with that number as a template parameter, so I can use it in template context, right? But you don't have to see that as a user. I mean, if you don't understand that's the point. You don't have to understand that, right? You know what's happening here, right? I mean, this is way better than standard get pointy brackets number, right? Indexing into a tuple. So in the Quasir library that I developed, which is kind of the first step in bringing real C++ to embedded, we try to abstract the interactions with special function registers. Now, what's a special function register? essentially, to the compiler, it's just a RAM address. But it's hardwired to actual features, right? Like if I want to turn an LED on and off, right? Well, that's a pin. And that pin is mapped to a register. So if I write a 1 into one of the bits in that register, it's going to turn it on, right? Problem with these special function registers is they're quirky, right? Like the hardware devs seem to have a very black sense of humor. Like, a lot of the time it is good intention. Maybe I have a register. When I read it, it automatically clears some of the status flags. Because, yeah, you read that, right? So now you don't have to clear them. But at the same time, if I'm not expecting that, and I'm reading a completely unrelated bit field, right? Because I've got a bunch of different bit fields in this 32-bit register. The way I'd read those would be, okay, read the whole thing and then mask off all the bits that don't interest me and maybe shift it towards 0 because only one of the bit fields is 0 aligned, right? If I do that, then I'm also clearing these bits, right? So if okay, somebody checked 2 lines of code into the repository. Oh, they're reading something new. Well, yeah, do I say merge or not, right? I have to go look in the data sheet. Are they inadvertently clearing bits? And if they are, then I have to go back and look in the code. Is that what they actually wanted to do or not, right? I mean, to put this into perspective, the data sheets of most of these chips are bigger than the C++ standard, right? And, maybe not quite as complex, but close, right? So, I mean, having this constraint of every time anything changes with regard to registers, you do like a giant code review. I mean, this is why we can't probably name any software from Siemens and they have as many people as Microsoft, right? This takes a long time. I mean, poor dev guys have to explain why their productivity is a couple of lines of code a day, right? It's legitimate though, right? And a lot of, it also fosters kind of a guess and pray mentality, right? Oh, I don't think that there's any reason to make a clear on read bit there. So I'm not going to go look because I have a date to meet, right? So, so what we're doing here is we're taking our mental model. I don't think of registers, I think of bit fields, right? And these names are cryptic. That's actually from the chip manufacturer. But, okay, wake up, right? Suspend. Wake up and suspend are in a register that has clear on read bits. So if I were to say read with those bits, I would get a compiler error, right? It would say you have to use unsafe read. And once I have to use unsafe read, well, then I know I only have to code review the unsafe ones, right? 95% of all the actions that I take are now safe. You don't have to look in the data sheet. You know what's going on, right? There's also bits where, don't ask me why, you write a 1 to clear it, right? I mean, these are usually hardware flags where the hardware will set it and you can clear it. So it's a mailbox, basically, in some concurrent situation, right? And so, but the problem is if you write a 1 to clear it, well, if you access unrelated bits, you're reading the register, changing the bits that interest you, and writing that back to the register. You would think all the bits that weren't part of my mask wouldn't change, right? But I'm writing that 1 that was in there back to it, which makes it 0, right? Again, something you'd have to look up in the data sheet, right? But our library knows this, and so if you say, don't access that bit field, it will write a 0 rather than a 1, regardless of what was in there, because I know if I write a 0, it won't change it, right? And if I want to clear it, if I say clear, it may actually write a 1, because I want to clear it, right? Clear that flag. This probably would still pass the Sean Parent test. It's not like vector bool. I mean, okay, I can't give addresses to bit fields, but this is a read-only construct here, right? As long as you can just read it, nothing goes wrong. So we learned that lesson, right? We can also index using the same bit fields because it's a unique type, right? And I know what type it is. I can pass it through my apply function to status. So I can still do that, right? The other thing is, as far as efficiency compared to handwritten C, none of this actually does anything. Only when it gets to here do I actually generate the code, right? So I can take all of those templated structs and all the modifiers of like read and write, adding information to what I want to read and write, and run it through a compile time algorithm, which is essentially a compile time sort and then a compile time fold, which merges all the ones that are next to each other and actually the same register into one operation. And the result is often an order of magnitude faster than you could do it in C, right? Because if you were to write the absolute fastest possible, you could do it in C at the exact same speed, right? But if you were to write that, no one, including yourself, would ever be able to read it again, right? But we don't have that problem in C++ because we're just feeding a code generator with stuff close to our mental model, and it's actually generating the code. The other thing we're using here is policy-based class design, right? I mean, this is the canonical example of policy-based class design, right? I have a hello world class, and well, what could you swap out in a hello world? Either the language you're saying hello world in, or the method in which you're writing hello world to the world, right? I mean, default would be standard output, but you could also just as well put it in a file or send it to the internet or whatever, right? So our implementation of hello world, okay, how do we send it to the world? T-shirt cannon, obviously, right? And what language? Well, hipster. Well, what's hipster? Well, you say keep calm and whatever before everything you say, right? And hipsters have to express themselves with T-shirts, so that's yeah. Anyway, so we're constructing this policy-based class, and we can drop in anything here and anything here, any combination of those, and it will work. The problem is this is absolutely ugly, right? And if we're thinking about a real policy-based class like the USB, class that we saw earlier, I mean, it has like 100 policy classes, right? Because you can configure all sorts of stuff. That would fill the whole page essentially here, right? So that's why policy-based class design hasn't really caught on in the same way that other things from 2001 caught on, right? Because it's ugly and it looks complicated, right? But we're C++ 11 now. We can just use auto, right? The type is here. So I make a factory function that builds me a hello world with whatever I put into it, right? And it's no longer a constructor. It's a function called make hello world. And actually in C++ 17, we can actually make this the constructor again. But okay, we're C++ 11 compatible now. We have to say make. But yeah, this is a lot cleaner, right? And if you think about this, okay, what if I had, more patterns, more policy classes? They would go here, comma, something else, something else, something else, right? And if I want to default them, I can make them defaulted in my factory, right? So the user doesn't have to know about the extra configuration possibility until they actually do it, right? Problem with that is, what if I wanted to use the default here, but did want to specialize that, right? Well, in C++, we just have default after the last thing that you said, right? And if I want to, if I have 20 defaults and I want to specialize the 19th one, well, I have to actually explicitly say what 18 of them are, right? This is a problem. Solution to this is name parameters, which are possible in C++ if you consider the fact that a copy assignment operator doesn't have to return the type of the class of which it's a member. So we can use that to make named parameters, right? We just pass whatever we got in back, wrapped in some, this was the name, and then put all those in a tuple, and at compile time sort that out so the user can index into the tuple and get the parameters that they wanted. We can even go a little bit further than this. We can say, okay, I don't accept something that's convertible to my argument type. I accept anything that fulfills this meta function, right? So I can accept all kinds of allocators, right? Or I can accept, anything that's a number, right? And not actually convert it to a double. I can also still accept positional arguments, right? I mean, I'm metaprogramming here. So if I get a bunch of stuff that wasn't named, I can say, well, does that map to my positional arguments? And I can also define rules about unique convertibility, right? If I have an argument and it's only convertible to one thing, I mean, okay, if that thing is like a C array, well, a lot of things are actually convertible to that. You might get false positives, right? But if you say, I need an allocator, and I don't care where you put it, probably your allocator predicate will only work on allocators, right? So we can do uniquely convertible. And this actually was done pre-C++11, like in Boost. Anyone tell me why this didn't catch on? Like why we're not all using this? Yeah, because they did it in macros, right? I mean, it's obviously an API fail if you have to give a comment where the name of the function is, right? There's actually some other problems with this, right? I mean, okay, the basic syntax is, you define your names, right? What can be a name parameter, what can have like an equal sign on the right-hand side of it, and you're passing things to it. And you define, some rules about these parameters. Problem here is return type can't depend on the types of my inputs, right? With a templated function, I can make the return type depend on the types of the parameters passed to me. And we need that because we need to make a factory function that gives us a special type depending on what users pass to us. So this doesn't work so well with policy-based class design yet because we didn't have such good tools. We have better tools now, right? Here, you can see what the function's called, right? You could also implement Svine, right? You could make trailing return, decal type, use these T's, right? I mean, it does look a little complicated, but if we're accepting a variadic amount of parameters of which we don't know the type, well, the only option obviously is a pack of arguments, right? But we take the arguments that the user passed to us, can work on them in normal ways. There are no macros here. We pass them to a name parameter tuple. And this is D-style syntax. We could also use pointies here, but this works too. First set of parameters is compile time known. Second set of parameters are the runtime parameters, right? So we're telling it what name parameters do I actually accept, and here what did I get, right? And it builds me a tuple with which I can index what are the parameters that the user passed to me. And so I will get what they passed or the default. If in my definition of a name parameter, I said there is no default, then I'll get an error if the parameters passed to me don't fulfill that. If they didn't pass me one of those, right? So I can call it with name parameters. Now this is how we did those vid-pid things, right? Because positional on giant chunks of data doesn't really work anymore if any of them could be default, right? But using this, we can make those kinds of factories. Sean Parent would kick me out of his office for this, I heard in his talk. But essentially, the only thing that we're doing is this iffy. All of this is standard, no macro hacking, no black magic, all standard template metaprogramming, except for misusing the copy assignment operator. And we're doing that in a way, in a class that has no other member functions, no other data, whatever. I don't think that's really going to cause problems. But it's very important to pass the Sean Parent test. I said I was going to get into the heap some more. The problem with the heap is it could be fragmented, right? And if you want to statically prove that in the worst possible fragmentation scenario, you still have enough RAM, like in desktop, we assume we have endless RAM. And most of the time we do, right? At least enough. But here we have tiny amount of RAM. We have to prove that we're not going to in any fragmentation scenario not have RAM, right? Because if your IBAG doesn't have RAM, that's not good, right? So it's not only that, but it's also like even if it has enough RAM, the timing of a new allocation isn't fixed, right? So your set of possible timing problems, like it works now, will it always work? Well, what's your set of possible timing stuff, right? And this is a problem on a lot of stuff, even new stuff like KUKA robots, right? They're very timing dependent. And sometimes those windows of when you can send a command get fuzzy because how is the stack fragmented, right? And this is terrible because you can't even document it properly. You can't really test it properly. Like, okay, most of the time in this window you'll get a response, but not always, and we don't really know why, right? Those kinds of problems. Essentially, if you think about the stack, the heap, what kind of objects are you putting on it? You have objects where you have, 0 or 1 of them, right? Either I have one or I don't. That's why I put it on the heap. In that case, most of the time, just putting it in a global variable or a singleton. I mean, people also hate singletons, but different domain guys. The critique of singletons is essentially it lives forever. Well, we always live forever, right? It's not a problem in our domain. It's a multi-threading problem. Well, we usually just have 1 core, right? Not so much a problem in our domain. It's not mockable. Well, you can actually make them mockable using traits tricks, right? They can be mockable. Initialization could be iffy, but our stuff is usually not like initialized with dependencies on other stuff. I mean, we're way less complex, right? I mean, if we had modern programming, like most programs that embedded would be like 10 lines of code, right? I mean, they're not complex things that we're doing on these tiny chips. So I think a singleton in this domain, not in other domains, but in this domain is very viable because, okay, you're using it always now, but it was probably part of your worst case scenario all the time anyway. We're only interested in worst case, right? And you also don't have the heap overhead or the fragmentation penalty, right? Because you have to add like several X to be sure that it won't in any fragmentation scenario fill up, right? And you don't in the case of global variables because they just go right next to each other and you know statically how big they are, right? The other thing is you have 0 to n, right? You have a number of packets, right? I could have 0, I could have many of them, right? Those map actually quite well to either pools or like the buddy algorithm. So this is another thing that we're working on, trying to build libraries that work well with those constraints. Threading and embedded. Okay, math. Wake up, guys. I have 6 threads, right? Okay, every hardware driver, if you write them blocking, will need a thread, right? So my UART needs a thread, my other UART needs a thread, my USB needs a thread. I have 6 threads. I also have some interrupts, right? These are not giant nesting depths, right? Function calls a function, calls a function, calls a function, right? 1 is already always there, right? So 4 more calls in an interrupt service routine, 9 more calls in a thread is actually, pretty small nesting depth. So how do we calculate this? Like how much RAM will my stack need? Well, interrupts, if there's 3 priorities, they could all interrupt each other at the absolute max nesting depth of each respective interrupt, right? Lowest priority runs to its max depth, gets interrupted by the next highest priority, runs to its max depth, gets interrupted again, and so on. And those interrupts could also interrupt any one of the 6 threads that each have their own stack, right? There's ways to get around this, but then interrupt latency increases. But just as a flat example, okay, so with this small trivial program, I have 15 plus 10 times 6, 150 stack frames. How big is a stack frame minimally? Okay, maybe I have no local variables. Well, work register 0 to 3 is pushed to stack on ARM regardless. I have to know how big my stack frame is, and I have to know where I'm going to return to. So 6 ints or 6 pointers, or however you want to think about 32-bit values. So I've got 900 pointers, and 4K of RAM is only 1,000 pointers. So I filled up my entire RAM just with the stack of this tiny program, right? And then you can get into, like, how did I even calculate this? How do I know max stack depth, right? I mean, nobody here probably calculates their max stack depth because with virtual addressing, it's no problem. It just adds another slice, right? Here we don't have virtual addressing. So how can we help this? Well, run to completion kernels, which, again, are a very different design pattern. We, as programmers, have learned in school to think in threads, right? I mean, it's very binary. Some people think in state machines, no matter if they're programming threads or not, because essentially everything's a state machine, right? And if you program in a state machine, as in my state is not implicitly on the stack, but it's explicit as state local storage, then I don't need multiple stacks anymore, right? Every routine in the state machine has its own state local variables, therefore is no longer dependent on the stack. So you just have to make sure not interrupt them while they're running, hence run to completion. And then, yeah, this other paradigm works. Kind of running out of time here. Boost MSM Lite by Chris Uziak completely sped up the whole state machine creation project time at compile time, right? It's like 100 times faster than Boost MSM. You can use like 1,000 states or something before you get performance problems. Whereas Boost MSM, it was like, okay, 30. Oh, you're going to go get coffee for that, right? So yeah, this is proof of my claim that we've gotten way faster with. And I think I think Chris could even actually make this again 5x faster. The syntax is old though, right? I mean, back then it was good that we had this kind of cryptic operator overloading syntax, but now we can do better because we can make we call it the lambda state machine, which looks more like this, right? Again, it's a function call, right? So state one has data, has entry, has exit. I can also like leave out entry and exit. This derives from that. The interesting thing here is the concept of a state chain, because threads are actually very linear, right? I mean, if we think of them as a state machine, everywhere where we sleep or block or wait for something, that's a state, right? We're going back to the operating system at that point. And we think of state machines as like the toaster example, where you could transition from any state to any other state, and in like the microwave toaster oven that's always used as a state machine example, you transition all over the place. There's not really like a chain, but most of the time, okay, I'm getting my database handle. And if I don't have the database handle, I'm doing rollback. Okay, I'm opening the database, waiting for the database, right? Okay, if I can open it, then I'm going to go forward. If not, I'm going to go backwards and roll back, i.e. close the database, right? Opening a database table, querying some value. If I encounter an error there, I'm closing that table, I'm closing a database, right? It's commit and rollback semantics, essentially. I mean, we do this with Rye. We do this with essentially, using destructors in stack lifetime objects to do the rollback. But we could also do that in a state machine, right? And if I'm going from here to there to there to there to there, I don't actually have to name all those states in between, right? So we can generate anonymous states at compile time, and then create these state chain semantics where, okay, if this guard fires, then I do this and then I do that, right? Default is an action. I can also say action equals something. I can use lambdas. I can use functors. If I pass this rollback, and then something here goes wrong, I go and do that rollback in reverse order when transitioning back to the original state, right? So this is a long transition from state one to a lot of intermediate anonymous states and then to state two, right? Yeah, I can do different kinds of guards. I'm not sure if this is very good syntax. We're misusing operators again. I think we actually even changed this since these slides were made. But yeah, we tried to implement this on top of Chris Uziak's MSM Lite. The problem is state local storage is a little more complicated than he supports. Because there's another complicated thing in our domain, another design constraint, deep sleep. Now, if we go into deep sleep as a processor, we essentially use no energy, like run for 10 years on a battery, right? Or 20 years. Probably the battery from internal leakage will empty before our thing actually uses the energy in there, right? So the problem is that RAM usually isn't persistent across a deep sleep. So if I deep sleep, some portion of my RAM will survive, and the rest of my RAM will be random data, right? And so it's very hard to program for this model. And hence, although many processors can deep sleep, most don't, right? Which is why batteries go dead a lot faster than they really need to, right? We could model this with a state machine very well, though. We could say, in this state, I can deep sleep, And all the stuff that's persistent is state local storage in that state. But that also means that we may need part of the state machine to be allocated somewhere and part of the rest of the state machine to be allocated somewhere else. And MSMLite doesn't support that. So we're kind of thinking about, how do we're probably gonna have to write a backend to do this right. So what did we learn? Embedded, completely different beast, right? Way different design constraints, way different things that we have to worry about, and hence we come up with very different patterns, right? A lot of these requirements are very uncompromising, right? Like you could make a lazy choice and say, oh, well, I'll just use the heap, or oh, I'll just use something that's non-deterministic. Well, that will work if your goal is bullshit bingo, but that won't work if your goal is actually a product that's going to survive a long time, right? That's not going to be just bought by early adopters that don't mind if they wake up freezing, right? If you want to actually sell to people, then you have to take this into consideration. It's a whole different beast when you do, right? But on the other hand, we have insanely powerful tools now, right? Like we not only can write our own code generator, we can also write essentially our own optimizer, right? Like that big sort and then fold left function we do in Quasar now, that's optimizing the code at compile time because we know more constraints than the compiler does, right? Problem is, I think this is a typical nerd problem, not enough hours in the day, right? We're a tiny, tiny company, right? Like most of my dev team is here. And we're not making any money off of this directly. We don't have a sugar daddy. So, this is our free time. This is some work time because we're trading innovation for profit, right? And so, yeah, I think there is a lot more potential if we were, this is basically what I presented to you here is, cumulative 2.5 man years, right? I think we could do a lot if we had a lot more man years. So what did we learn about appies? Well, okay, this was just a composite. We can be a lot more intuitive because we have new tools, right? Zero cost versus teachable versus writable, readable is not such a trade-off anymore, right? We can make way better syntax because we have new tools. And because of policy-based class design, essentially, there's other ways of making customization points. We can implement open-closed things that are extensible and flexible. A policy-based class can do way more things, can mutate in way more ways than if you were using virtual functions, right? You're not bound to some tree-like hierarchy. You're not bound to the other constraints that you have. Even if you don't think of the runtime cost, right? So, yeah, I hope a lot of C++ developers join the cause. At this point, metaprogramming experience is kind of a requirement. We do a hardcore metaprogramming course as part of onboarding if you want to work for us. Yeah, I think I should probably go on to questions at this point. Pass back to the host.
Okay, thank you very much. Thank you, Odin. I see one sentence that you wrote in your presentation that's embedded is a different beast.
Yeah.
And I know this beast will grow because it's 3S, smart, sexy, and small. Okay,
Yeah.
now open the discussion. We have a little time, so I think that 3 questions.
Thanks for great presentation, first
Thanks.
of all. And the question is related to the API for memory map device you showed at the beginning, almost.
Yeah.
So my question is, do you handle such cases, because there are some quirks, for example, when you do such
Real
access.
embedded guy. I like it. Yeah.
So the question is, for example, if you do the folding of the read writes, etc., as you said, how do you handle, for example, cases when you have to wait, for example, 1 bus cycle when you access some peripheral device and it is explicitly said in documentation? So how do you actually...
So you have to do A before you do B, kind of a thing?
Yes.
Yeah. You can set sequence points, and we respect those.
And do you do it, for example, because you said you parse the XML file from the device manufacturer, do you pre-generate it with the flags you have in this, let's say, static map of types?
Yeah. We put everything in there that we can find in the. We actually put a little more information in there sometimes. Like there's an extension format for the XML. If we, in a perfect world where we had time, we would put the Python generator code in the repository, as in like a Travis hook, so that you modify the extension format and it generates you new C++ code. Because the goal is that you don't need any external tools, right? So yeah, we put, if like there's, set to clear, there's clear to clear, there's toggle, there's also some tricks that you can do with regard to threading safety, right? On some chips, there'll be can transmit as part of a register and can receive is also part of a register, and those are running in different interrupt context, right? I'm transmitting from the main thread and I'm receiving in an interrupt. And so, if my interrupt interrupts at the exact right spot in my main thread and I'm modifying this register, the modification that the interrupt did could be reversed. But what I can do there is I can narrow the scope. So I can say I only want to work on 8 bits. And the TX stuff is in a different byte than the RX stuff. So even though it's a 32-bit register, I can constrain it to work on 8 bits. And I don't have this race condition. Or I can do stuff with I/O. Like I/O is, global variable, right? I have a port and everybody's using it, right? So I also have these same race condition problems. But on most chips, you can actually access I/O in an atomic manner because they have a toggle register, right? So you take what I want to write, you read what's in there, and then you make your change to that. You store your change to that in there, and you write that to the toggle register, and that just changes the bits that you want. If somebody else is interrupting you, changing different bits on that port, it won't interfere with your changes. So we do all the information plus a little bit more.
Is it on the web, as I understand?
Yes, quasir.io.
Thank you very much.
Yeah, at the beginning you said there are not so many well-known people working in the field. What would be your fix? How can you make it more known?
Well, our average is like we meet one guy every conference that works on this kind of stuff, and we're trying to remedy that because I wasn't actually too nice to you guys this time. Most conferences I have to spend like half my talk explaining what bare metal embedded is, and then I explain what we're going to do, because you can't assume that people already know things about bare metal embedded. So if you think, okay, every conference has one or two, I know Bartek is running around here somewhere, 1 or 2 microcontroller talks, and half of each of them is explaining microcontrollers. That's not very efficient. So in all honesty, we were drunk and thought, we'll make our own conference. And then we got sober and thought, we actually could do that. So the EMBO conference, as in Embedded in Bochum, it's in Germany in February, embo.io. If you're on bare metal systems or you're a super template metaprogramming nerd, that would also be interesting for you. But mostly embedded guys, small conference, but with good speakers. Come and we'll talk about it. Or if anyone's watching this on YouTube, contact me.
Okay, I see that you give your email, and we can contact you every time. Yes.
Oh yeah, even the smallest question, like if your compiler is giving you an error and you don't understand it, send me an email, yeah?
Oh, we can see that we have a live debugger normally.